investigation here, you're going to get things set up like this. We're just putting the desks on each other gives you some more space for the spring to stretch. And depending on which spring you have, if you leave the desk on the ground, the mass might touch the ground, and then we can't do our experiment. These little coat hooks on the desks provide a nice little place for your ring stand point. Now this, where it hangs at rest, is the equilibrium position of the mass. And what you're going to do is get it oscillating. You can just let it go up and down. And then as the mass is oscillating, you're going to measure the period of oscillation using the stopwatch. Now, for this one, it moves pretty slowly, but for some mass spring combinations, the mass will bounce up and down faster, so it might be harder to see when one period is. So to increase your accuracy, it's better to measure multiple periods. So you can start at maximum height, so right there-ish, and 1, 2, 3, 4, 5. Maybe measure 5 periods, and then divide the time by 5, and then you can find the period of your oscillation. And our goal is to figure out a formula for that period. To do that, each of 3 groups are going to measure one of 3 different quantities. We're going to investigate what effect changing the mass has, what effect changing the spring has, and what effect changing the amplitude of oscillation has. Now, in any good experiment, if you want to determine what causes what, you need to only change one thing. So, if you're the group that is investigating the effect of mass, then you need to use the same spring every time, and you need to give it the same amplitude of oscillation every time. If you're the group that is determining what effect the spring constant has, then you're going to use 5 different springs, but you're going to want to keep the same mass and the same amplitude every time. And then the group that's measuring, seeing the effect of amplitude, you will want to use the same mass and the same spring every time. Now the group that is testing the effect of amplitude should go ahead and use this spring. It's the only one that's this long. And because the spring is just longer, it's easier to vary the amplitude for this one than it will be for some of the other springs. So you can you can hold your tape measure just like this, and then when you start it, you can lift the mass however far, and whatever, so it's resting here right about at 71 centimeters more or less. Look at where the center of it is. Or actually, it doesn't matter at the top or the bottom, just as long as it's in the same place. The top's about 68 centimeters. So if I go up to 60 centimeters, then the amplitude of oscillation there would be 8 centimeters. So you can adjust the amplitude like that. For everyone else anyone who's not seeing the effect of amplitude, you still want to have your tape measure to check that you're doing the same amplitude of oscillation every time. That doesn't mean you start from the same height. That means you move the same distance from this middle position. For the other 2 groups, the group that is measuring mass, make sure you use the smallest mass first, because the smallest mass will give you the least spring stretch when you just hang it, and therefore allow for the smallest amplitude. So if you want to use the same amplitude every time, you want to pick the one that has the smallest possible amplitude first, so that you can make sure you have the same amplitude every time. For the spring, it's the opposite. You want to use the spring with the highest spring constant first, because it will stretch the least, and you'll be able to give it the smallest amplitude. The one last thing I want to say right here is that when you're timing the period of your oscillations, you don't need to hold it here and say ready, set, go, and start. You can just get it moving and then start whenever you want to. It's just going up and down. It's just doing its thing. The period isn't changing. So I can, wait until whenever and then start whenever I want to. So it's when it reaches a maximum, go, and then time. But you don't need to start the timer at the same time you start the mass moving. To investigate the pendulum, we're going to do things pretty similarly. We're going to set up our bar on a desk, but now we'll have string and then a mass to attach to the end of the string. Here's for those of you that are, if you're swapping out the mass of the string, it's an easy way to hook this up without tying it so that we don't have to wind up cutting our strings. If you slide this loop through so that the mass is sitting on the string, having troubles, here we go. Slide it through so you just got the mass on the string, and then open this up, feed the other end of the string through it, and then the string will hook nicely onto the mass. Oop, this string is fraying though. The string will hook nicely onto the mass, and it's secure, but it's not tied in a knot, so that we can easily just slide it back off again when we want to. Then we can use the string again later. We can use the same mass, and everything is shiny and happy, except that this string is fraying, so now it's getting caught. Okay, there we go. So we can unhook the string and use it again later. Now, for the pendulum, we're going to be doing something very similar to what we did with the mass spring system. There are 3 different quantities that you might be investigating. You might be varying the mass, you might be varying the length, you might be varying the amplitude. In the case of a pendulum, the amplitude is an angle, not a distance. So you can use a protractor to either make sure your amplitude is remaining consistent, or if you're varying amplitude, then measure what amplitude you're starting at. So we put this on here, and then we can displace this the appropriate angle, and then have it oscillate back and forth. Now remember, as per what I showed you regarding the pendulum, once you get past about 15 degrees, the motion of a pendulum is no longer simple harmonic. So whichever group you are, make sure you keep your angles under 15 degrees. The one other thing that I want to make note of is that the length of this it would be the length of the string if we were dealing with a true simple pendulum, because a true simple pendulum has a point mass on the end. So the mass would all be located right there at the end of the string, and it would be lovely and shiny and happy. But that is not the case. Our mass is not a point mass. So when you're measuring the length of the pendulum, your best bet is to measure from the middle of the bar, because that's where the rotation is going to happen, down to the middle of your mass. So that's about 38 centimeters on this one. But you want to go from the middle of the bar to the middle of the hanging mass. Yeah, and then other than that, you just swap out the masses, swap out the strings, depending on what you're measuring, and then do the same kind of power regression we did for the, you will do the same kind of data analysis for both parts, which is something called a power regression, and I'll show you what that is in the rest of this video. For the mass spring and pendulum investigations, I want to show you what you're going to do with your data here. In both cases, you'll have data where you'll have periods, 5 periods, and then you'll also have 5 values of whatever quantity it is you're testing, which could be mass, spring constant, or amplitude for the mass spring system, and it could be length, amplitude, or mass for the pendulum. So what you'll do is you'll take that data and go Stat, press the Stat button, Edit, and you're going to put that data into your list. We did something like this for the spring constant, when we were looking at Hooke's law. But for that one, we were expecting a linear relationship. So just like we did there, you put the data for your independent variable, which is what you're changing, which could be mass, spring constant, length, whatever, into L1, and put the data for your dependent variable, which is period, in L2.
And then you're going to go stat, calc, and this time we're trying to figure out what kind of relationship it is. So we're going to do a power regression. The power regression will see what exponent best fits the relationship. I'm going to do a power reg, L1, L2. Now, I don't remember what this data was, so I don't know what this will come out to. Wow, that's a really good fit. And it'll give you an equation in the format ax to the b. So y, in every case, is going to represent your period, and then x is whatever variable you were changing. So if you're changing the mass, then x is going to represent mass. And what you're looking for here is specifically what the exponent is. I don't remember what this data was, but that exponent's pretty close to -2, so the relationship might be an inverse relationship with the square of whatever that variable is. And your correlation coefficient will show you how good of a fit that is. So you want to look at the exponent and see what it is. If it's close to 1, it might be a direct proportionality. Close to -1, it might be an inverse proportionality. If it's close to 2, it might be proportional to the square. If it's close to 1/2, it might be proportional to the square root. So you just want to see what that exponent value is. And then your R value, of course, tells you how good of a fit this is. If R is close to 1 or -1, then that tells you that this curve is a very good fit. And from this, we're going to figure out proportionalities to try to derive an equation. For example, let's say that when we collect all of our data and perform our regressions, let's say we find out that for mass, we get that period is equal to something times mass to the 2.005. And then when we vary the spring constant, we find that period is equal to something times spring constant to the -3.01. And then for amplitude, we find that period is equal to something times amplitude to the 0.499. We can put all this together and say, oh, well, period is proportional to mass to this power. That's almost 2. This is pretty close to -3. This is close to 0.5. So we can say period is equal to something times, what do we have? Mass squared times square root of amplitude, 0.5 power is a square root, over k cubed. And then we'll do something also to figure out what this constant is. But I will tell you this isn't what the equation actually is. But we can figure out what format the equation has based on these results.